Okay, so again, we're looking at the relationship between valence electrons and the arrangement of the periodic table. There are so many patterns on the periodic table that you're going to notice, and it's because of those patterns that we're able to remember the characteristics and the properties of the different elements and make predictions about how they're going to react. So the first thing that we're going to look at, hopefully you've got the essential question written down. I'm going to go ahead and go to slide number 2. We'll look at this, and then I'm going to ask you to take just a moment to see what patterns come to mind for you. So here's what I did. I took 2 elements from group 1A. Remember, group up and down, and group 1A is that first column. And so I took lithium from period 2 and sodium from period 3, so period 2 and period 3. I wrote down how many electrons they have, and then I also wrote their electron configuration. Okay? Then I did the same exact thing for group 2A. I found the element that was in period 2 of group 2A, and then period 3 from group 2A. So I did that consistently for all of these groups. Now remember, the A designation, I kind of think of it as the alternative numbering system. It's the numbering system we use when we're only looking at the representative elements. So remember, 3A is the same as 13, 4A is the same as 14, 5A, 15, and so on. Take just a second to write down one of the patterns that you notice as you look at these electron configurations and group numbers. Sublevel and number of electrons are the same if they're completely filled. Yes. So let's take a look at group 1A and notice that both of these elements end with the same sublevel and number of electrons. Same sublevel. Remember, the first number is the energy level, this letter is the sublevel, and the number is the number of electrons. So both of these end with S1. Both of these end with S2. So that's a great pattern. All right, and each group, the number of electrons go up by 1. Okay, yep. So you've got 3 electrons in lithium, and then if we go to group 2A, there's 4, and then boron, there's 5. So they do go up by 1. There's a difference of 8 electrons in each group. Yes, I happen to pull them all from energy levels, or excuse me, periods 2 and 3. And so that pattern works great for those 2 periods. If we go to the next period, then it starts to get a little wonky on the right side. But that's a good observation too. So one of the things that I want to say one more time, and hopefully you'll see this connection. This is from period 2, and the last energy level that we see electrons in is 2. This element is from, let me get my flashy pointer here. This element is from period 3, and energy level 3 is the last energy level where we see electrons. Okay, and that's consistent. Beryllium's from period 2. 2 is the highest energy level. Magnesium is from period 3, and 3 is the highest energy level. So we can see that there's a connection as we go across the periods. Every time we move to the next element, as we move from left to right across the period, it increases by 1 electron. And if we look at the groups up and down, they end with the same sublevel and number of electrons. And, another one for the periods moving across is that the highest energy level matches the period that they come from. So knowing those patterns, And we might discover a couple more as we go along. I'm going to go ahead and go to slide 3. So if you're following along on your own screen, you can do that. So what I did was I made a periodic table that has all of the ending electron configurations written inside the boxes. So for example, with lithium, if I go back to the previous slide real quick, lithium ended with 2s1. So I put 2s1 in that box. Beryllium ended with 2s2. So I put 2s2 in its box. So if we look at the entire electron configuration for all of the elements on the periodic table, and then take the last configuration notation and put it in the box, now we really see a pattern. Okay, so again, it was mentioned that as we go across the period, notice that we're adding another electron, so from 1 to 2 electrons, and then 1, 2, 3, 4, 5, 6 electrons. And then even if we go in this center section, notice how they all line up. All of these are D1s. All of these are D2s. See how it says D2 up here? And it increases by 1 as we go across. So D1 all the way through D10, and P1 through P6. And then down here in the bottom 2 rows, we've got F1 through F14. The other thing that we notice is that the s orbital, which can hold 2 electrons, remember s can only hold 2 because there's only one of those orbitals. Notice that there's 2 groups that end in s, s1 and s2. And if we jump over here to the elements on this side of the periodic table of the representative elements, P has 3 orbitals. Each one can hold 2, so 2, 4, 6 electrons. And notice that they line up on the periodic table so that there's 6 groups that end in P. D has 5 orbitals, which means 10 electrons, and there are 10 columns that end in D. And then F, we didn't do any of these electron configurations, but these go from 1 to 14, and that's because the F sublevel has 7 orbitals, 2 electrons each, for a total of 14. Okay, so because everything in this group ends with S, I'm going to go ahead and advance to the next slide. This is the one that has the colorful periodic tables on it. So now what I've done is I've color-coded the ones that have the same ending. And notice over here, I've got helium. Helium really does belong in this group because all of the elements in this group have completely full shells or completely full orbitals. And helium, with its 2 electrons, completely fills up 1s. So it really does belong here, over here. However, when we're talking about these electron configurations, it also belongs over here because it ends in S2. So I've got helium here and I've got helium here. Now, notice how they form these nice neat blocks. So we're going to call this red block the S block. These all end in D. So, hey, let's call that the D block. These all end in P. So this is the P block. And of course, down at the bottom, we've got the F block. We often use these blocks to describe the location of the elements because they are so descriptive. We know that, for example, that only the elements in the S and P blocks have predictable numbers of electrons in their outermost energy level. Okay. With our other color coding, we had the step line, and we had some transition elements, and we had some metalloids that kind of overlapped a little bit. And with this, we have a nice, neat distinction between the representative elements and the transition elements. S and P follow the rules, D and F not necessarily. Open my periodic table, the one that you guys also have, if you got one in class. And let me just show you that you got those same letter designations with each column. So up here, we've got several things that you can look up about each group. So it's group 1, or we can also call it 1A. We'll talk about valence electrons in just a minute. We'll get to charge in the next unit. And then the sublevel, all of the elements in this group end with a sublevel S1. So if I want to figure out what electron configuration lithium ends with, the period number is going to be the energy level, and then it's going to end in S1. So if we follow down and across, we get 2S1. And this one would be 2S2. Okay, and that works for the P groups as well. Okay, so if I go back to our original slide here, another thing that you'll see on this periodic table, it's on the right side. On your periodic table, the one that I gave you, it's on the left side over here by the period numbers. But this is the filling order. So remember I told you I would always give you the filling order. There's 1S, and then 2S, and then 2P, 3S, 3P, 4S, and then because of that overlap that we talked about with energy levels 3 and 4, it goes to 3D and then 4P. So if I know that, for example, silicone ends with 3P2, everything up to that point has to be filled. So I know that the S sublevel can only hold 2 electrons, P can hold up to 6, and D can hold up to 10. So if I know that silicone ends with 3, so period 3, P2, I can go over to the filling order and I can backfill. In other words, I can fill up everything up to 3P2. So it'd be 1S2, 2S2, 2P6, 3S2, 3P2. And it saves a lot of time. You don't have to draw all the arrows and transfer it to the electron configuration. And here's where we're going to define valence electrons. Please write this down. Valence electrons are probably the most important particles when it comes to talking about how atoms react with each other and form bonds. So the valence electrons are the electrons in the highest outermost energy level. So remember with the Bohr diagram, we actually numbered them 1, 2, and 3. So 3 is the highest energy level. It's also the one on the outside. And then notice how the electrons fill up. Energy level 1, energy level 2 is filled. So they're very stable. It's not until we get out here to energy level number 3 that we don't necessarily have a stable energy level. And those are also the first electrons that are going to come in contact if they bump into another element. So these electrons, the valence electrons, are the ones that are available for bonding in a chemical reaction. These inside electrons don't like to bond. They're happy where they are. It doesn't take a whole lot of energy. But the ones out here are usually more stable if they are involved in a chemical reaction. Just to kind of compare, we've got 3 energy levels, 1, 2, 3, and we have 1 electron in this highest energy level. And so we call that the valence electron. We look at the highest energy level and then look at the number of electrons in that highest energy level. Here's the 3rd energy level, and there's 1 electron. Okay, let's use this same technique now to look at the number of valence electrons in these other groups. So again, we're going to look for the highest energy level. So I have electrons in energy level 1 and energy level 2. So 2 is the highest energy level. So let's circle that notation, and we see that it contains 1 electron. If we go to sodium, which is also in group 1, 3 is the highest energy level, so that's the one we're going to circle. Okay, and it looks pretty similar for group 2. 2 is the highest energy level, so there are 2 electrons that we would call valence electrons, and same for magnesium. Now, we would have to pay attention a little bit more when we get to the group 3A elements. These are the ones that are across the transition elements. In other words, groups 13 through 18. And when we get over there, yes, it ends in P1, but P1 is not the only electron in that highest energy level. We've got electrons in energy level 2 in the S sublevel also. So when we get to group 3A, we have to circle S2 and P1. So all 3 of these electrons, 2 plus 1, all 3 of those electrons are considered valence electrons. Okay, same thing for the aluminum. And that happens to be the case now for everything in from group 3A over to group 8A. We'll have to circle 2 sets of notations because at those highest energy levels, or the biggest energy level numbers, we have multiple sublevels with electrons. All right, so now if we count the electrons that we circled, okay, group 1's easy. Group 1 has 1 valence electron. Again, you don't have to copy this chart. It might be a good idea for you to write down one example of an electron configuration from, let's say, group 1A, and maybe one from one of the 3 through 8 groups, just so that you can see that the valence electrons are at the highest energy level. And sometimes that's 1 notation and sometimes it's 2. Notice when we get to group 2A, we see that we've circled 2 electrons. The superscript, remember the number that sits up above, is the number of electrons. All right, when we get to group 3A, we circled these 2 electrons and this electron for a total of 3. And that's true for this one as well. So group 3A has 3 valence electrons. Okay, well, we can do the same thing for the rest of these. 2 plus 2 is 4. Sorry, that gets covered up when I move my cursor. And 2 plus 3 makes 5. And I think you can see the pattern here. Okay, so group 8A has 8 valence electrons, and one of the things that we'll talk about when we talk about bonding is 8 valence electrons is the maximum number you will ever see for any element. They'll never have more than 8 valence electrons. All right, so we've discovered something else that's important here, and that is that the number of valence electrons, or those all-important electrons that are available for bonding in a chemical reaction, match the A group number. All right, so let's go to this last slide. And I've got them written in here. So I have a row here that says valence electrons. Notice that group 1A has 1 valence electron, group 2A has 2. So if we looked at the Bohr diagrams for these, there'd be 2 electrons in that outermost circle. Notice that we don't have any valence electrons written down for this D group, and that's because they aren't as predictable. For example, copper can have 1 or 2 valence electrons. Iron can have 2 or 3 valence electrons, depending on the conditions. So these aren't as predictable. So we don't write them here. And then we get over to group 3A and 3, and then through 8A, 8. So to summarize, here's the relationship between the electron configuration and the arrangement of the periodic table. The number of valence electrons, remember you can abbreviate electron E minus, matches the A group number. And number is another one that you can abbreviate with a hashtag. All of the representative elements, and remember the representative elements are the ones in the S and P block. So again, there's S, D, P, and F. S, D, P, and F. All of those elements in the same group have the same number of valence electrons. So for groups 1A, 2A, 3A through 8A, all of the elements in the entire group have the same number of valence electrons. So, since they're responsible for bonding, representative elements in the same group, up and down, will react similarly.